All right, so proposition 47, second last of book 1, is Pythagoras' theorem, which says, in Euclid's language, in right-angled triangles, the square on the side subtending the right angle maybe I'll draw the picture. I think I'll just take up this whole board with the diagram. Maybe that's the best way to do it. So I'll draw my right-angled triangle. I want to make sure I have room for everything. Yeah. ABC.
I guess me doing the second part means that I don't have to draw the diagram.
Yeah, we'll see. Maybe we have to draw it twice. I don't know if we use both sets of boards. It might be awkward otherwise, but we'll see.
Yeah, true. Yeah.
In right-angled triangles, the square on the side subtending the right angle, so that's the side BC, is equal in area to the squares, that is the sum of the areas of the squares on the sides containing the right angle. So that is the squares on the sides BA and AC. Okay. We'll do a few constructions and then I'll move over to the other board. I don't really have a lot of room to write. I need to make sure I don't obscure the squares. Actually, I've kind of already, yeah. I'm going to do this on the other board. I think it'll be better.
I was going to say, Dan, you actually only need one of the squares, right?
One of the squares.
Yeah, so like you draw the two sides to this side, that side, and then the hypotenuse side, right? So you need a square on the hypotenuse side, and then you can just work with the smaller square. The other square is just the same, right? Like they just repeat the argument on the other side. You know what I mean?
Oh yeah, I guess that's true. Yeah, that's true.
Yeah. That would make the diagram slightly less, fewer lines, I guess. Yeah.
Yeah, I guess that's true. All right, so by proposition 46, we can describe on BC the square BDEC. So this was A, B, C. I don't know why this square gets a name for all the vertices and the other two just get named by the diagonals, but all right.
Yeah, right.
It's like this is special. He's the hypotenuse. He gets names. DE. And similarly, on BA, AC, the squares GB and HC. I think I'll put them all in.
Yeah, it'll totally fit now that you're on this board, right?
Yeah. So let's try and make them look plausibly square-like. Now I've drawn that line not quite in line with AC. That was an accident, but it will serve a purpose because we don't know that that is actually in a straight line. That's part of the proof. So that's GF. So at the moment, we've just constructed these squares on these sides, and that's all we know. All right, so that's proposition 46. Now we draw some lines. Through A, let AL be drawn parallel to BD. And I guess that's actually a proposition, right? I didn't look up which proposition that is. Maybe you could have a quick look, Kenneth, if you've got the book. We did prove that we could do that. And let AL be drawn. Sorry. And let ADFC be joined. So L is defined by where the line parallel to BD passing through A meets the line DE.
Yeah, so you're dropping a perpendicular from A to DE, right? Let me see. How do I find this? I'm just scrolling back.
What did I say? AD and FC. Okay, AD, yep, and FC. So it might look like a bit of chaos at this point, but what we're trying to do is pretty simple in the end. We're trying to find this area inside this area and find this area also inside this area and show they add up to the large area. To do that, the sort of summary of the argument is we're going to relate this area to the area of a triangle by proposition 41, and we're going to relate that triangle to this triangle and that triangle to this square, or rather to this square. And we're going to do the same over here. We're going to say this area is the same as the area of, oh, no, I haven't drawn the lines for that one. So we'll draw a few more lines and run a similar argument for showing that this square can be recognized as this area here. So we're going to use these connections between triangles and parallelograms to relate these areas. All right. Since each of the angles BAC, BAG, so what we're about now, I believe, is proving that GA and AC lie on a straight line, because without that, we can't use the argument I just outlined, which relies on, remember, parallelograms and triangles with the same base and with sort of tops on the same line have a relationship between their areas. That's proposition 41, and that's the workhorse of this argument. But to apply it, we need to know that this is actually a straight line here. Okay, but that's true because since each of the angles BAC and BAG is a right angle, it follows that with a straight line BA and at the point A on it, the two lines AC and AG, they're not on the same side. And they make adjacent angles equal to two right angles. So that's enough. By proposition 14, CA is in a straight line. with AG. And for the same reason, BA is in a straight line with AH. Where do we want to swap roles, Kenneth?
Have you 14? I'm just trying to look at my notes. Maybe now? I don't know.
It would kind of make sense to swap when
Yeah,
we just start hitting 41 over and over again.
Yeah. Oh, actually, in my notes, we're hitting 41 now, but maybe you haven't gotten to it yet. I was just checking.
I think
Yeah, that
maybe
sounds good.
maybe I'll finish putting in the lines that you'll need to use, and then I'll hand over.
Cool. Sounds good.
Okay, so I'll do a bit over here. All right, so since the angle DBC is equal to FBA, let the angle ABC be added to each. All right. Yeah, this is really a bit awkward without the diagram.
Yeah.
Maybe we can just fill around the diagram a little bit. It's probably worth having 2 copies of it.
Sorry, I wasn't attached. Were you saying something?
Oh, yeah, no problem. I said maybe you can redraw the diagram on the other board so that for your part it's also visible without having to swap between these boards.
I'll do that silently while you go.
Yep. Okay, so DBC is equal to FBA, right? Because they're both right angles. Let ABC be added to each. So they remain equal. So the whole angle DBA is equal to FBC. It's by common notion too. So let's locate these angles. So DBA is this angle here. And FBC is that angle there. So they're equal. We're aiming to prove that these two triangles are actually equal. So for that, we just have to argue that that side is equal to that side, but they're a square. That's a square, so those are equal. So note FB is equal to AB. And, well, this side of this triangle is also equal to that side of this triangle because it's a square. So what did I say? BC is equal to BD. So we have two triangles, FBC and ABD. There's an angle, the angle between those two sides, ABBD, FBBC, which is equal, and two sides are equal. So by proposition 4, way back at the start, the two triangles are equal. That is, all sides are equal, all angles are equal, correspondingly. All right, I think that's probably a good place to hand over.
Cool. Yeah, actually, that's what I was thinking. That I don't know whether you can hear me. Yeah. Sorry, I was a bit too far away. Yeah, that's what I was thinking actually. This is like the geometry part, and then now we do the slicing and dicing of areas.
Yep. Okay. I'll walk over here and you can continue. Oh, I guess you can take the orb.
Cool, thanks. Cool. So now, yeah, let's continue. Hopefully, I can fit this on the board that we have on the left here. I'm just trying to walk my avatar over. There we go. So, yeah, so Dan's proved for us that the two triangles we constructed on the new diagram here, ABD, and maybe I'll even indicate with a pen, ABD, which is this guy here, and FBC or CBF, this guy here, right? These two are congruent triangles. We're going to use these to relate these to the areas of parallelograms and or squares, and show that what we claimed is true, which is that the squares, the areas of the small squares add up to the area of the big square. Okay, so carrying on, so I'm going to do this. You know, I have two arguments here that are basically the same, so I'm just going to kind of write it in the same line. So the parallelogram. So now we're going to relate areas of parallelograms to the triangles, right? BL. So we're going to look at the parallelogram BL, and also look at the square GB. All right. So that has double. Hang on. Double the area of the triangle, and two different triangles corresponding to whichever case we're talking about. So I'm actually going to write this in a slightly nicer way. So the triangle ABD for the first case, and FBC in the second case, right? Since they have the same base, and the base is BD and FB, right? And are between the same parallel lines. The same parallel lines. And the parallel lines are BD and AL, and this is GC and FB. Okay, so let's just go to the diagram and take a quick look at what this means. So we're looking at BL. Let me just click on the diagram with this. So look at BL, right? BL is this thing here, right? So claim that this rectangle or parallelogram, in this case, we actually never used the word rectangle, so I'll just stick with parallelogram. So this parallelogram has twice the area of this triangle here, this one, because it's got the same base, right? The base is FD, this one, and they're between parallel lines. The parallel lines are obviously these ones, right? AL and BD. I won't draw them in. Maybe it's okay, right? These two. Okay, so that's fine. The other conclusion we want to make is that the parallelogram BG, which is this guy over here, it's actually a square, that has the same, well, double the area of this little triangle here. Okay, and because they share the same base, right, and the base they share is FB, which is this line here, and they're between two parallel lines. And the parallel lines we're talking about are at GC, which is this line here. Remember, we proved that this is actually a line, not just two line segments stuck together. So we can say that GC is a line parallel to FB. Okay, and so therefore that square has twice the area of this triangle. So you can already see, you know, the argument forming, right? We've shown previously that these two triangles are congruent, the same, they're actually exactly the same. Consequently, they have the same area. And so what we're actually going to say is that, well, because of this, this square has the same area as this parallelogram. So we're already halfway there, right? So remember what we were trying to do was to show that the sum of the areas of this guy and this guy is the same as sum of, well, actually same as the area of this guy. And we've actually cut this square in half, not in half, in a way like this, such that this area maps to here and this area maps to here. So it's pretty cool. Okay, so going back to the board, that's the first part of the argument. I've kind of just, explained on the diagram what's going on. So let's write it out. So now the areas of BL and GB are the same, right? So therefore, the areas. Oh, I forgot to say previously, the proposition we're relying on here is proposition 41. So this argument is because of proposition 41. So therefore, the square GB, the square GB and B and the parallelogram BL are equal to double the area of the same triangle, right? The areas of BL and GB are equal to double the area of congruent triangles, or the same triangle, equal triangles. We can be a bit lax here because we're just talking about area. And so since double of this same things are equal to each other, they're the same. And this is, I think, another combination that maybe not numbered, but definitely something that we may have used before, but we're using here. So since double of equal things are equal, the areas of BL and GB are equal. Okay, so I think from here, we don't have to do much more work than this because the argument on the other side is totally symmetric. What I'll do is I'll draw the constructions in, maybe in a different color, and we can see what's going on. So the other construction on the other side, right, is going to look like this. We're going to draw the line from A to E, and we're going to draw the line from K to B. Right, and so what we're going to do is we're going to say we're going to say that the let me just indicate here we're going to say that the area here is twice the area of this, and we're going to say that the area of this square is twice the area of this. And then we're done because we've basically just repeated the same argument on the other side with this other square AK, and then we're done. So I'll just write this on the other side with some concluding remarks, and that's it. Okay, so we repeat the same argument. On the other side, I guess on the square AK. And I guess the other parallelogram is, I'll call it CL, just because it's easier, CL, right? And so what we're going to be doing is, ACE is BCK, right? So 1, 2, CL is equal to 2 times ACE. These are areas now, and AK is equal to 2 times BCK, and so 3, we're going to conclude that CL is equal to AK. So I'm being a slightly sloppy here with this because it's essentially the same argument from what we had earlier, right? One was the congruent triangle bit that Dan did. This CL equals 2 times the area of ACE. That's really what we've done over here. And 3 is this part here, right? Talking about how doubles of equal things are equal. And so, finally, I'll finish off in a little space that we have down here. Since the areas of BL and CL, all right, so there's a final line, since the areas of BL and CL is equal to the areas to the area of the square BECD. Well, unfortunately, I'll have to go to the next page. BECD, and oh, I change colors when I change boards, of course. And BL is equal to ABFH. CL is equal to ACKH. We are done. Okay. Yeah, so the last thing is that the BL, right, is the left half of the square, the right half of the square is CL, right? Basically just saying that, yeah, this is essentially just saying that BL and CL, they add up to the square. BL is equal to this, and CL is equal to this, so we're done. Cool, and that's
Nice.
Pythagoras' theorem.
Yeah, I really like that argument. It's such a
Yeah, really nice, really nice.
yeah, that's the reason it's a famous theorem, I guess. But it's the proof could have not been as nice as it was somehow, even though the result is clearly fundamental. But you really get a sense of understanding why it's true after having seen this.
Yeah, so I actually talked to a friend about this, and they said that they did this at school, and they had some memory of triangles and Pythagoras' theorem. I don't know whether this is like, you know, a fake memory or not, but certainly some people have done this. I mean, I don't think I did this. By the time I saw Pythagoras' theorem, you know, we were using algebra, and you know, there was probably some contrived proof using trigonometry or
Right.
something like that, which, you know, depends on analysis and things like that. And, you know, this is really much more basic, right? This is just Euclidean geometry, right? You don't need any of that limits and stuff. So so it's really nice to see a proof just from these methods.
Yeah. I think maybe we should push through Proposition 48 quickly and then be done with Book 1. I hope Edmund can give us a few more minutes into the next session. What do you say?
You know, I actually didn't even realize there was a proposition 48. Sure.
Well, maybe I'll just do it then. It's kind of, it would be a bit pointless to leave it on its own session because it's very easy once we have Pythagoras. So I think we'll just rush through it and then we can declare ourselves done. Okay, you can disconnect and I'll...
Yeah.
All right, Proposition 48. It's basically something like a converse to Pythagoras' theorem. It says how to recognize a right-angled triangle by this statement. So if in a triangle, the square on one of the sides be equal to the squares on the remaining two sides, I've noticed myself become kind of fall under the spell of Euclid, and I'm not saying area anymore. I'm just saying equal. Yeah, I can't resist. The angle contained by the remaining two sides is right. So it's exactly a converse to the Pythagorean theorem. All right, and this is a nice argument as well, not very difficult given what we've done now. Okay, so we're going to consider a triangle and suppose that it has this relationship, but that we don't know that BAC is a right angle. This is, so we're assuming I won't spell it out. I'll just say, suppose the hypothesis for the triangle BAC. So what I mean by that is suppose that the square on the side BC is equal to the sum of the areas of the squares on the sides AB and AC. And then we claim BAC is right. That is, it's a right angle. All right, for let AD be drawn at right angles to the line AC. And with AD equal to BA. So we can draw that. It's not cited in the book. I don't remember the exact proposition, but we can draw a line of a given length at a given angle. And let DC be joined. As I did. Since DA is equal to AB, so we're going to relate these two triangles, right? So since DA is equal to AB, the square on DA is equal to the square on AB. So let the square of AC be added to each. Well, by Pythagoras, when we add the square here to the square here, since this is a right angle, we get the square on the side CD. I lost this line here. Let the square DAAC be added the square of. Okay. AC be added to each. By proposition 47, the 1 is equal to the square on DC. So I've added the square of AC to the square on DA. I get the square on DC. And the other right. Okay, yeah, right. The hypothesis is that the square on the side BC is equal to the square on the side AC plus the square on the side AB. So to summarize, I've argued that the square on this side is equal to the sum of these two squares, which is equal to the sum of these two squares, which by hypothesis is equal to the sum to the square on that side. So I end up showing that the square on the side DC is equal to the square on the side BC. And the other is equal to the square on the side BC. Now I'm going to square root both sides and say they're equal. So the claim is that if you have two lines and the square on both of them, the squares on the two of them have the same area, then the lines have the same length. You can prove that by constructing the shorter line. Suppose otherwise, construct the shorter line on the longer one, erect the squares by proposition whatever, 46, and then you'll get a contradiction where a whole is equal to a part. I won't write it out, but so you can deduce from these squares being equal that the two sides are equal. So we deduce that DC is equal to CB. But then by proposition 8, we're done, right? Because we've proven the side DA is equal to the side AB, the side AC is common, and the opposite sides have the same length. So by proposition 8, the angles have to be equal. By proposition 8, BAC is equal to DAC, which is a right angle. So we're done. So we have both directions in Pythagoras' theorem. And that's it for book 1.
Nice.
Whoa! Thanks, Ethan.
That's pretty cool. Nice.
That's really neat. Okay, thanks everyone for joining us in this journey through book 1 of Euclid. I guess we're going to take a break for a little while from Euclid and do some algebraic geometry, but I think we'll return and continue with book 2 at some point. Any questions or comments about those last 2 propositions or book 1 in general?
So I have a question which is not related to this. Are we keeping the same time slot for algebraic geometry? We probably need more than half an hour, right?
Yeah,
well, we talked about time slots, but yeah, maybe not this time slot.
Yeah, I guess we'll probably have a while where we may use this time slot just to discuss what we're going to do and put together the curriculum.
Yeah,
so maybe maybe just for next week we'll keep this time slot and you and I can discuss that, and anybody else who wants to show up can do. How's that sound?
That sounds good.
Awesome. All right, so thanks to Edmund for waiting, and we'll move over to SLT for his talk on main theorem 2 of Watanabe. Thanks everyone.
Cool.
Yeah, thanks Ethan. That was extra special. All right, yes. It's actually surprisingly smooth. I guess it's there's a particle effect